including the intercept already into the beta. So this is like putting a hyperplane down and saying everything on one side of the hyperplane is we're going to classify as a 1, and everything on the other side is -1. So you look at lots of linear classifiers in 701. Maybe I should write that 8 sub beta because it just depends on these parameters beta. Now, one difference between regression and classification is the following. In regression, when we wrote down the empirical version of the risk, we could just take the derivative and set it equal to 0, and we got the least squares estimate. So minimizing the empirical risk in regression was easy. The problem here is minimizing this risk over beta. Can we do that? If I think of this now, if I make this, let's make it a function bigger. I try to minimize over all betas. Is that easy minimization? No, why? Yeah, this is a bad function, right? It's not convex, it's not even smooth. So it's a hard function to minimize. So what we often do is sneak in a surrogate loss function. We replace the 1-0 loss with something a bit nicer. So as I put in the notes, it's actually helpful to rewrite the loss a bit. So if you imagine again that I generate an x randomly, I hand it to you, you apply your function h, and now I get the y and I can see, I get it right or wrong? That's what that's evaluating. But that's equivalent, given the way that we've written things at least, that the probability that y times h of x is negative. Why is that? Because we coded y as +1 and -1 conveniently. And our classifier is going to output a +1 or -1. Y is a +1 or -1. So obviously, if I get it right, then it's either plus, plus, or minus, minus. Either way, it's positive. So getting this correct is saying that it's positive. If I make a mistake, one of them is negative, one of them is positive, it's negative. So these two statements are equivalent. And it's helpful to see it that way because it really depends on this product, y times h. Where if I replace this probability with expected value, it's the expected value. I wrote it like this, where alpha is just the product. The point here is that a good way to picture all these things is to think of this product, y times h. That's a real number, right? We're getting on a real number. This linear classifier is going to be a number. Then we're going to take the sign of it eventually. But what comes out of the classifier is a number. Sorry, that's what I just said is wrong. Everything I just said is wrong. That should say, this should not be h. Well, this should be, let's call it a linear, let's just call it times. It's the sign of this thing that matters. So it looks like this. In other words, what I meant to say was, we get out we run our linear classifier, it has a sign, y has a sign, and if the signs agree, I get it right, there's no loss, and if the signs disagree, I make an error. So this is the 1-0 loss function that I'm drawing here. This is 1 or 0. And the point being, this is not a smooth function, it's not a convex function, it's not a nice function. So in practice, we might try to use some nicer function, maybe a smooth function, maybe a convex function, in place of the 1-0 loss function. Yeah. So this H correlation, again, maybe I should call it alpha. Alpha. So there's various nice functions we could use to approximate this. And the one you probably spent quite a bit of time on 701 is what is, in some sense, the smallest, so to speak, convex function that lies above this. So you want to get it as close to this as possible to convex. It will look like this. That's called the hinge loss. So the hinge loss, because it looks like a hinge function. So that suggests, instead of minimizing this, let's minimize the hinge loss. So a surrogate way to try to find a good linear classifier is to minimize. And what is this function? It's actually just 1 minus yi times and the plus just means if it becomes negative, then truncate it at 0. And then typically, for a variety of reasons, one also adds in regularization as well. The point is that this is a convex function, this is a smooth function, so this is something that can be minimized. And so you get out a linear classifier, but now you can actually do the minimization easily. Do you remember what the classifiers are? So that's the support vector. So there's the geometric perspective of support vector machines, but I think an easier way to think about it is you're just substituting 0 loss for a convex surrogate loss. So that's something that will come up lots in the class. Yeah.
Is hinge loss minimal convex surrogate of the 0, 1 loss?
Yes. This, of all, I believe that if you take the input over all convex functions that lie above the 0, 1, then you get this. But there are other surrogates. So like add a boost you probably learned about is implicitly using the exponential loss. And in fact, the one that probably gets used most often in statistics is based on linear logistic regression. So let me remind you about logistic regression. Logistic regression says, well, let's take the probability that y is equal to 1 given x, just like in linear regression we picked a simple form for the regression function. Here we try to pick a simple form. Let's call it m sub beta of x, and I think you remember it has this form. So that gives us a parametric model, and we can write down the likelihood function. Now we can think about these as Bernoullis. I'm flipping a coin. It's either coming up heads or tails, plus 1 or minus 1. But the probability of success is not some fixed number. It depends on beta and x. So if I write out the Bernoulli likelihood, remember, what's the Bernoulli likelihood? It's p to the y and 1 minus p to the 1 minus y. Right? P if it's heads, 1 minus p if it's tails. Actually, we have to do a little bit of recoding here because instead of having a Bernoulli that's 0 and 1, which is how we usually write Bernoullis, up to now we've been using y to be plus 1 or minus 1 because it was convenient to do so. But if I take zi to be yi plus 1 over 2, that converts it back to 0, 1. Okay? And so now I can just write the Bernoulli likelihood as the probability of success to the z and the probability of failure to the 1 minus z. So the probability of success is m. And the probability of failure that is a nice concave function. Actually, if you take the logarithm of that, the log likelihood is concave. It's easy to maximize. You did logistic regression in 701, right? And what was the algorithm for finding the MLE? Reweighted these squares, right? So to start the R evangelical conversion process. So of course one line in R to get the ML in R. It's just GLM. GLM, see if I can remember, Y triple X family equals binomial. Remember correctly. But I'm sure MATLAB has a logistic regression thing with it. But you know what? If you look at the log likelihood, take a log and do a little bit of algebra, you can see what is it you're minimizing is another surrogate function. You can rewrite it. It corresponds to replacing the 1, 0 loss with this loss function. Did you do that in 701? Did you show that was a good one? If you didn't, you should go through the algebra. It's just a couple lines of algebra. That maximizing the log likelihood is equivalent to, just by rewriting it, minimizing an empirical loss. And the loss is this thing, which if you plot it, just looks like this. You can just think of it again as an approximation to the 0, 1 function, but it's a nice, smooth, differentiable function that's easy to minimize. So there's two ways to think about logistic regression. One of them is I'm just putting down a simple parametric model for the probability of success, and then I'm dealing with the likelihood function from that model. The second way to think about it is I'm trying to find a linear classifier. I don't want to deal with the 0, 1 function, so I pick this nice, smooth approximating function. Those are two different ways to think about what you're doing when you're doing logistic regression. Either way, you get a beta from what you get a linear classifier. So those are two common ways to get linear classifiers, logistic regressions for vector machines. There are other ones I'm sure you covered as well. Okay. So, I think I covered then everything that was supposed to be kind of a review of stuff that you saw in 701, 705. First of all, any questions about anything we talked about?
Like label the axes on.
Label the axes. Oh yes. So this is y times, I guess, beta transpose x. And this is the indicator function for whether that's less than a 0 or bigger than 0, the loss. So whether y is equal to the indicator for whether y is equal to the classifier. Any other questions?
So in the notes, some of the places you have on the board this L.
Yeah, sorry about that. I stuck in the classifier when I meant the linear part of the classifier, so let's just go through and make sure that that all makes sense. Because this is supposed to be the margin, as it's called, the 4 that got converted into 0, 1.
I guess there are results that say when you minimize the surrogate, you're pretty close.
Okay, good question. So there's a paper by Mike Jordan, Martin Wainwright, and I'm forgetting John McCullough maybe, and it's in, I think it's in JASA, which is the Journal of the American Statistical Association. And what they show is, if you minimize the surrogate loss, how good are we doing at minimizing the true loss? And they have a lot of results about that. Basically, the short answer is yes, it still does pretty good. In particular, if one of them is consistent, if it gets you in the limit a good classifier, so does the other one. Of course, it may not get you the optimal classifier and so on. Yeah, there's a lot of results about that. I'm sure there's other papers as well now. This was the first one, I think, that did it in detail. But there's probably others that talk about it as well. So that's Jordan. Wainwright. If you just Google Jordan Wainwright surrogate loss, you'll find all the papers probably and all the subsequent papers since then. Any other questions? Okay. Was there anything, no one's going to have the nerve to put up their hand and cancel this, but was there anything there that I covered that I said, you know this would 701, and you actually didn't cover it? It's good for us to know, like, oh, they assumed we knew, for recognition, but we never actually took that. So if there's things like that that we're assuming that you didn't really cover, it's good to let us know. Otherwise, I'll just assume you know it.
There's a difference between covering and covering it well.
There's a difference in covering it and covering it well. Okay. Ooh. All right. So when we use some of these things, we will then make sure we talk about the details. So for example, when we talk about lasso, we'll start from scratch and make sure we do all the details, even though you might have seen it before. That's what I'm going to do. For example, I'm about to do non-parametric density estimation, and although I think you have seen some of it before, I'm going to start from scratch because I realize that 701 covers things quickly, and so you might not have done things in detail.
I think everything except for logistic regression was covered in fairly.
You didn't do logistic regression?
I think we touched on it, but not in.
Okay, so probably at some point when we do sparsity, we'll probably talk about sparse logistic regression, and we'll probably talk about it in more detail then. Okay, good. So let's go on to topic 1, which I hope you've either downloaded the notes or got your laptop or whatever. We're going to talk about non-parametric density estimation. And so, yes, you did see a bit of this in 701 and perhaps 705, but we're going to go into some of the gory details. So what's the basic problem? Well, I have x1 to xn to be sampled from some distribution p, and we're going to assume p has some sort of density function, little p. And the goal is to estimate little p. Actually, let's do an aside. Suppose I didn't want to estimate the density. Suppose I wanted to estimate the cumulative distribution function. Remember what that is. It's the probability that x is less than or equal to little x. So I'm following the standard statistics convention. Capital X means the random variable, and little x is a particular value. So you think of little x as 17, or 3, or 2, it's a number. This is random. And then as I vary this, we get this function that looks like this, goes from 0 to 1. Suppose I wanted to estimate the CDF, not the density. It's not very often you want to estimate the CDF, but suppose you did. Let's just start with that. How might you estimate the cumulative distribution function?
Isn't there an empirical formula?
Yes. So the natural thing to do, let's suppose these are your data. These are data points. They're just supposed to be random. I don't know how random they look, but these are random data points. And the natural thing to do is at any given x, let's say here, I'm trying to estimate the probability that the random variable is less than or equal to this. So a natural thing to do is just count the proportion of observations. So that's called the empirical distribution function. Say fn of x. It's just the number of xi's less than x over n. So the empirical looks like this actually. It's 0, then it jumps by 1 over n at each data point. And the reason why I wanted to mention this as an aside is one of the cool things about the empirical CDF is that if I look at the maximum difference between the empirical CDF and the true CDF, this goes to 0. In fact, it goes to 0 pretty quickly, as it turns So in statistical language, that says the empirical CDF is a consistent estimator of the true CDF. And here's the cool thing about this, there's no assumptions. This is true for any CDF. We're not assuming that it's normal, or that it's Poisson, or exponential. It doesn't matter what it's in. For any CDF you can create in the entire universe, the empirical CDF is consistently, this is convergence in probability. In fact, I'll tell you, you can even say something stronger. The probability that this is bigger than epsilon, probably the maximum distance between those two things is bigger than epsilon is less than or equal to 2e to the minus 2 n epsilon squared. So it's not only going to 0, it's going pretty fast. That will probably look now a little bit familiar written that way. Does that remind you of VC theory? Okay. It's because of VC theory, which we'll talk about in detail later. Okay. Yes?
So is there a reason to use anything other than the ECF?
Than the CDF?
Than the empirical CDF?
Well,
If you're
that's an
assuming-
interesting question. There's going to be a lecture called Foundations, where we'll talk about some of that stuff, because my quick answer is no, but there's people who disagree. The empirical is very simple, and it's got these nice properties. All right. The reason why I wanted to mention this, though, because this is kind of a side thing, was we didn't have to make any assumptions at all. This is completely non-parametric. There's no parametric assumption. Unfortunately, the density function is a little bit more delicate. We're going to have to make some assumptions, but we don't want to go all the way. We don't want to assume it's normal or some parametric family, because those parametric assumptions are very restrictive. So we want to do this non-parametric variance with as weak assumptions as possible. But we can't treat it like the CDF, it turns out. We can't just assume, oh, I'm not going to assume anything. So this is going to be a kind of in-between sort of situation. There's no completely non-parametric estimate of a density. And actually, before we proceed any further, so I'm sorry, I'm doing a lot of side comments here, but at least that way you get your money's worth coming to class, right? If I didn't have extra stuff to say, you could just read this. All right, because I want to mention this, something that might occur to you is, why don't we do maximum likelihood? So what is the likelihood? Assuming that it's IID, the likelihood for given density would just be, and I could say, well, I know how to do maximum likelihood. The parameter now is a function, but okay, why don't I just maximize the likelihood over all density functions P? Why is that a bad idea? What is the MLE going to be?
You'll just have like split all the
Yeah. Because I can take a density very thin and narrow over each data point, and it'll be a density, it'll integrate to 1 because I can make it narrower and narrower, but taller and taller. So in some limiting sense, I'm just getting spikes over the data points. That's not a very nice density estimator. Densities intrinsically are going to require some sort of smoothness if we're going to be able to estimate. So maximum likelihood, at least the way we usually do it, won't work. All right. Let's start with an example. This, on page 2, I'm going to show you an example. The top left is a true density function, so I constructed this density, so I know the truth. In real problems, of course, we never know the true density. That's known as the Bart-Simpson density. And what I've shown you are 3 different estimators. These are called kernel density estimators. This is not kernel in the sense of reproducing kernel Euler space. That's a bit of confusion. The word kernel gets used in different ways. This is not a reproducing kernel Euler space estimator, although actually it could be written as one, but we're not in that land right now. This is a different use of the word kernel. And there's a tuning parameter in there. And the top right shows you what happens if I don't smooth enough. There's going to be a tuning parameter that controls the amount of smoothing. And what we're seeing is the top right is an undersmooth density. The bottom right is showing you an oversmooth density. We've lost all of the structure. And then the bottom left is something that's actually pretty good, just right. So there's going to be some difficulties here about, we're going to have to do some sort of smoothing operation, and we're going to have to decide how to choose those tuning parameters. So let's try to formalize the problem a bit, though. I've got an unknown function, x, and somehow I'm going to produce an estimate, which is a function, of x. And how I design an estimator and how I evaluate it is going to depend on how we decide to measure what good and bad means. So again, there's, as always, there's many choices as possible. But I'm going to use the most common one again, which is squared error. On the homework, you'll explore a different loss function. So, but our goal, so this will be the loss, and the risk will be the expected value of this. Let's be careful about something. Now, the randomness here, where is the randomness here? It's not in the integral over x. That's just measuring. Here's the true density. Here's an estimator. At each x, we're measuring the distance, and then we're adding that up. That's why we're integrating. The randomness is in the fact that p hat has been constructed from the training data, so that it's hidden. The x1 to xn are kind of hidden in here, but that's where the randomness is. It's a random function. Little x is not random. This is a dummy variable, so you make it even. This is a random quantity. I take the expected value. It's not random anymore. That's what I want to make small. So what we'll see is there's a million methods for doing this. And in each of these methods, there'll be a basic construction, a basic way to construct the estimator. Then there's always going to be a tuning parameter. The tuning parameter is going to control how smooth we're making the density, and that's going to create, as we'll see, a bias variance trade-off. If we undersmooth, we get high variance. If we oversmooth, we get high bias. And so we're going to be in that world of trying to balance that. So let's start with the simplest estimator, which are histograms. All right, that's the simplest estimator. I think we can do histograms in like primary school, right? So we all know histograms. And just to keep things simple, let's keep everything. I'm assuming the sample space is the unit cube. There's nothing special about that. It's just going to make everything easier here. So the data, say, fall in this set. I'll draw it 2 dimensions. And the histogram is just what you think it is. We divide this. I'm going to just do regular histograms. So we're going to divide this into cubes. And each cube, the width of the cube will be h. So h is our tuning parameter, the width of the bins. And so we'll call these bins, this is say B1, B2, and so on. So ultimately we have, let's say, capital N bins. So what is N? N is going to be about 1 over h because there's about 1 over h on each axis, and then there's d dimensions. So you know how histogram works, is all you do is you just now take the data, which are in here, and then each bin we just count the number of observations, right, and we get the proportion. So the histogram estimator is defined to be p hat. I'll put a sub h here to remind you that there's a tuning parameter. And that's, let's write it this way. It's theta hat j over h to the d. This is for x in bin number j, where theta hat j is the proportion. It's just the proportion of observations in bin j. So just to make sure the notation is clear, I'm looking at some particular x, let's say here, and it's in some bin, let's say d sub j. And all I'm doing is I'm counting the number of observations. So this is the proportion of observations in that bin. Why do I divide it by h to the d? So it integrates to 1, right? Okay. I can write this, it's a little bit annoying to write it like this. I can write it, I can get rid of this if I just included an indicator function. So I'm going to write this as the sum over all bins times the indicator. So let me just be clear about the two different indicator functions here. This is just telling you that x is in one and only one of the bins. So this is 0. So if x is right here, this indicator function is 0 everywhere. It's only 1 when you're in that bin. So I'm just saying here the other theta j's are irrelevant unless x is in b here. That's just another way of writing this. Okay. This theta hat j is itself a sum of indicator functions, but this is for a fixed bin, and now we're summing over the data points. We're counting how many data points are in that bin. I hope I didn't make it more complicated than it has to be. This is just the ordinary histogram where you have a step function over here keeping track of the number of observations in each bin. That's all it is. All right, that's fine. So like I said, probably, grade 6 or 7, you use some histograms. And doesn't seem like a big deal, but we want to go a little bit farther than primary school and say, well, we can actually estimate the properties of this estimator. Now, in order to do that, we have to say something about what assumptions we're going to be making about the density. So what we want to be able to say is how good is this estimator, this density estimator, but it's going to be with respect to a certain class of distributions. Actually, it just occurred to me, I forgot to say, why are we doing density estimation? Why are we doing density estimation? I meant to say that. There's a lot of reasons why we're doing density estimation. So one is when we talk about clustering later in the class, a lot of non-parametric clustering methods are based on first doing the density estimator. A lot of classifiers turn out can be built from density estimators and so on. So density estimation is often just the first step into doing something else. So I should have said that in the beginning of the class. But when we want to ask how well it's doing, we have to say, well, with respect to what kind of assumptions. So the assumptions we're going to make for our analysis are the following. As I said, we can't use the set of all density functions. What I mean by that is there's no unit, well, yeah, you're not going to get a good estimator if we just assume density, any density function at all. We're going to use this class of densities. We're going to assume that the density satisfies the following smoothness constraint. Namely, that it's Lipschitz. So this is the set of all densities P that are probability density functions. So of course they integrate to 1, the non-negative, but they satisfy this Lipschitz bound. P of x minus P of y is bounded by some constant L times the distance of x minus y. That's kind of a minimal smoothness condition, right? It says there can't be infinite jumps in the density. We're not going to assume that L is known. We're just going to assume some finite L exists. Yes?
So this isn't like regression where we're assuming that the true function can be anything, we're just trying to find the closest linear approximation, here we're actually assuming the real
Well,
function is.
that's actually a good question. So what does it mean to make this assumption? So it means a couple of things. One is, we are going to assume at first that the true density is in this class so that we can say, suppose it is in this class, does it have good properties? How well is it doing? What's the optimal bin width and so on? Now, when you really analyze data, do we really assume the density is in this class? Well, probably not, because we don't really know what the true density looks like. So it's more like saying, well, if it was in this class, we can say that it has the following properties. But for doing theory, we are going to assume that it's actually in this class. This is a little bit different than the linear regression case, because in linear regression, there's no reason we would assume a true regression function is linear. The set of linear functions is a tiny fraction of all the functions in the world. Whereas this is a very rich, infinite dimensional class, so it's a little bit less unreasonable to make an assumption. But it is an assumption. Any other questions? So what I'd like to do now is say, let's suppose we use this histogram estimator to start with. We're going to improve on it shortly. For now, we'll use the histogram. Let's try to figure out the properties of the estimator. So in particular, what are the bias and variance of this estimator? Notice, by the way, that what is theta hat j? Theta hat j is the number, sort of the proportion of observations. What is that estimating? Theta hat j is obviously estimating the probability content of that cube. That's the true parameter that theta hat j is estimating. You can think of it as like a coin flipping experiment. Every observation either falls in min j or doesn't. And so it's Bernoulli. And it has a success probability of theta j, and we have the usual estimate of that theta hat j. And we know from our elementary statistics that the mean of theta hat j is theta j. And the variance of theta hat j, you remember that? It's theta j 1 minus theta j over n. So somehow we want to transfer that knowledge into something about this density estimator. Let's define, first of all, the mean of the density estimator. So I'm going to write P sub h of x to be the mean of the density estimator. This is at a fixed point, x. But it's easy to see what that is. It's, the only thing random here is this thing, right? So the mean of this is theta j over h to d. So the only thing left in terms of bias is, how do I relate this to the true density? So let's just subtract. Let's do that. So if we look at e of x minus its mean, all right, that's e of x minus mean, which is theta j. But what's theta j? Theta j is the probability dj. But of course, that's just the integral over dj. Right? So I can write this as the integral over bj, p of u, du over h to the d. And look, I'm integrating over, say, u. This doesn't depend on u, so I can bring it inside the integral column. In other words, somewhere there it is. Let me just say again what I did because there's a typo in this. Look at the first integral. P of x du, that doesn't depend on u, so I can bring it up front and I get just the integral du dj, which is the volume dj, which is h to the d. That gets canceled out by that. And so I get back this. And then the second one I'm just copying. But there should be an integral over dj there, which is missing. It's missing in everything that follows. So, all right. We're almost done with the bias analysis because now, to get the bias, I want to get the difference between, I'm just going to take the absolute value first. So p of x is less than or equal to the absolute value is less than or equal to 1 over h to the d times the absolute value of this thing. But wait a second. Look at this. This is, what are we doing? We're taking one of those cubes, and I'm looking at p of x. Here's x. Here's some other point u in the cube. I'm just taking the difference of p of x and p of u, where x and u are 2 points in the cube. Thanks to the Lipschitz condition, we know that how much can p change over there? It's just the distance of this times L. The maximum distance in a cube is, what is it, root p? It's L times h. Yeah, root p. Wait, it's wrong. I dropped the term somewhere. Let's just look at this. So this is L times h to the d. H to the d. Oh, I see. Yeah. Sorry, there's a term missing in the notes. A lot of mistakes in that. But let me say exactly what I'm doing. This thing I'm applying the Lipschitz bound to. Okay. This. The Lipschitz bound says, well, this is a cube of size h. The farthest any 2 points can be in here is root d times corner to corner. Here there's a 2 missing. And then the Lipschitz bound has an L in it. Where's the definition? Yeah, L times the distance. Okay. When I pull that out front, what am I left with? I'm left with the integral of this cube. The integral over a cube is just h to the d. And then there's an h to the d on the bottom. And so this gives me L h to the d. Which, by the way, I'm just going to write it like this for the moment. Whenever I write less than or equal to 12 means I'm throwing away some constants. So L and D are constants here. The bias is order h. What we just, or at least we upper bounded the bias by something we'll see. Next thing. So, okay, we've now answered one question. What is the bias? It's bounded by something constantly. Now we'll do the variance. So the variance of p hat is the variance theta hat j over h to the d. The h to the d comes out and gets squared. And theta hat j has variance theta j 1 minus theta j over n. And this, what is theta times 1 minus theta? That's at most a quarter, right? So that's 1 over 4 n h to the d. I just called it a constant c. And finally, the risk, which is the integrated loss. Now we use the fact that remember what the expected value. Remember the bias variance decomposition, right? The expected value of that squared is equal to the bias squared plus the variance squared. And we have upper bounds for the bias and variance. This is less than or equal to some constant times x squared, some constant over everybody with me? I just computed the bias, the variance. We know the bias squared plus the variance is the mean squared error. And when I integrate over the unit cube, it doesn't change anything because none of those bounds depend on x. So there you go. In this class of Lipschitz densities, we have a bound on the risk. And you can see the bias variance trade-off. When I make the bins bigger, not surprisingly, the bias gets bigger. Right? But if I try to make the bias smaller by making it smaller, look over here, you see that the variance goes up. So we explicitly see the bias variance trade-off. If you plot this as a function of h, it's going to look like this. There's going to be an optimal h. In fact, I can just take the derivative of this with respect to h and set it. Oh, question, yes.
What happened to the 2D and exponent?
Oh, I've now started putting constants in. Because I'm just caring about this as a function of h and n at this point. If I minimize this over h, I'm going to get, again, up to constants. Okay, so now that you know I'm getting lazy about constants, up to constants, we're going to get h is, let's write it like this thing, is basically 1 over n in particular, in one dimension, that says that the optimal bin width is 1 over n to the 1/3. This is an example of how a little calculation shows you something that you'd never guess intuitively. Right? If somebody said, what do you think the optimal bin width is for a histogram? You would never go 1 over n to the 1/3. Right? You have to do the calculation to see it. Ryan?
Just to clarify, in case people were confused, I think the question was, what happened to the h to the 2d in the exponent? That's not a constant. So you couldn't necessarily just drop that, because it's another h to the d. But you have to make a tighter bound on theta.
No. I made it, that's a typo. Why did I do that? That should actually say,
Instead of bounding theta,
no, you're right. No, I made a mistake. You're right. Sorry. There's an h to the d up here. Thanks. 1 minus theta j is less than 1. Theta j is the probability of a cube. The probability of the cube can be no more than the volume of the cube, or of the order of the volume of the cube, which is h to the d. Thanks. And that got rid of the, yeah, sorry, I misunderstood the question. That gives you 1 over n h to the d. And that's critical. That's not a constant. Right? Let me just say that again. Theta j, let me show you this explicitly. Theta j is the probability over a cube. The probability density function of this Lipschitz is bounded. So this is less than or equal to some constant times the volume of the cube. So up to a constant, this is just the volume of the cube. And so that's what happened to this one. This theta j got replaced with h. This one gets upper bounded by 1. That kills off one of the h to d. That's critical or we get the wrong rate. Thank you.
Yeah.
All right, to summarize, we have an upper bound on the risk, and we know something about the optimal bandwidth in this sense, that something of this order is the optimal bandwidth. This is not too useful because I've tossed away lots of constants. You couldn't actually analyze data with this. And if you tried to recover the constants, it really wouldn't be that helpful because those constants depended on things like L, Lipschitz bound, which we're assuming there's some Lipschitz bound. We don't really know what it is in practice and so on. So this is not meant to give you a practical method yet.
It makes sense, right?
Choose to
Because
begin with. We're just trying to get some theoretical understanding of how this thing behaves. Is this okay now? Nobody can do it. By the way, now that I've found the minimizer, I can plug this back into this formula that we have here and say, how does the mean squared error behave? How does the risk behave when you put in the boundary down? And if you do that, here's what you get. If the risk behaves up to constants like, let's just write it as big O, that takes care of the constants, 1 over m to the 2 over d plus 2. Now our kind of simple analysis is all of a sudden revealed a lot of information. If you're using a histogram, and if you pick the best possible dimwit, this risk measure, the way it's going to go to 0, is 1 over n to the 2 over d plus 2. Again, let's think about the case when d is 1. So that says it's going to go to 0 like 1 over n to the 2/3. Now, I want you to put yourself in the mindset that can you live a little bit earlier, last century, and you thought of this great thing called the histogram.
no, because
You
it's a
invented it.
function.
You do this risk analysis, and you say, look, the risk is 1 over n to the 2 over d plus 2, or 1 over n to the 2/3. Now the natural question you should ask yourself, and this is something is really important in general machine learning, is you're always excited when you come up with a new method, as you should be. But now you got to ask, is this as good as I can do? The way we will answer that later in the course is through minimax analysis. What we'll show later in the course is this theorem that's on page 4, which says you can't do any better than that, at least under these assumptions. That is, let's take a look at what the theorem says. The theorem says, if I look at this expected loss function. Okay, so that's the estimator minus the truth. Now look at that expected value. Now I say, what's the worst it can be over this class script P that we define? It's going to have all these Lipschitz. And now I ask, suppose I want to make that upper bound as small as possible. I want to make the worst case behavior as small as possible. What if I can make the minimum over all possible density estimators? And what we'll see later in the course is there's techniques to compute this, which is kind of surprising at first because taking the info over all possible density estimators, even ones you've never dreamed of, somehow we can get the minimum, and it's, again, up to a constant at least. We're worried about the rate here more than the constants, okay? And it turns out it's some constant times 2 over 2 plus v. Lo and behold, that matches this upper bound. So we'll see later in the course that proving this is non-trivial, but it's really helpful information because it now tells you your search is over, right? If this had not matched, you go, oh my God, I got to come up with a better estimator if you converge at this faster rate. But now you've learned up, now there's no point in me now spending the next 5 years trying to dream up new estimators, at least not for this class of distributions, because no estimator is going to go to zero faster than that. That's why this minimax stuff in calculator is useful theoretically. At least, again, theoretically. There's a lot of practical things we still have to get to, which is like how would you check how would you find a good bin with the practice? We'll get to that. But we've now successfully kind of covered a lot of ground in terms of understanding what is the histogram doing, what is its properties, how well does it do, can you do any better? That's kind of the train of thinking that one wants to have. In fact, the plan now is I want to switch right over to a more commonly used estimator, which is the kernel density estimator. And we're going to do the same thing. We're going to define it. We're going to compute its bias, its variance, and then we're going to show that under certain assumptions it has this minimax optimality. It can do better under particular assumptions. After we do that, we're going to come back to the question of how do you pick these tuning parameters. So I'm kind of deferring that question until we've covered the different methods. Okay. Another thing I want to defer is we're going to talk about how would you compute a confidence interval for this function. It's always good practice to not just have an estimate. Here's an estimate of something, but you want to know something about how sure you are about the estimate. You have a confidence interval around it. And that's coming later in the notes too. For now, we're just contenting ourselves with, we have an estimator, we have a bound on its risk behavior, and we know it's, in some sense, minimax optimal. So that was, in some sense, we covered a lot of material very quickly there, a lot of concepts very quickly at least. So I want to just pause before we go on to kernel density estimation to make sure you're not confused about anything. Are there any things you'd like me to clarify?
That's the best we can do, like why we bother.
Why bother with kernel? Because that's the best we can do relative to this class. You might want to change the class. But also, I don't want you to take, the theoretical analysis gives us insight, but we also don't want to be too serious. There might be other practical advantages, quite apart from this theoretical considerations. One of them is that a histogram is very unsmooth. And for a lot of practical reasons, we might want to have a smoother density estimate. Kernels are much smoother. So, yeah, when I say it's the best you can do and we jump up and down and celebrate, keep in mind that that's under very particular assumptions. So no, your search isn't quite over yet. Any other? All right, so let's go to kernel density estimators, which are probably the most commonly used density estimators. Now, I said earlier that the word kernel is used in many different ways. When we talk about reproducing kernel covert spaces later in the course, the word kernel comes up. And just to avoid confusion, we'll call those types of kernels Mercer kernels. Right now, I'm talking about a slightly different use of the word kernel, so I'll call them smoothing kernels. Different. They are very closely related, but it's better right now to keep them kind of as separate ideas. So these are smoothing kernels. What is a kernel? Let's do the one-dimensional case first. So a kernel, for right now, is going to be a function k, and we're only going to require that it be symmetric, that it be integrate to 1, and that it be smooth. So a normal density would be a kernel. In fact, I drew 4 kernels for you in page 5 of the notes. So the first kernel is called the boxcar kernel. It's smooth everywhere except, you see, it's not smooth at one point. So when I say smooth, there's different amounts of smoothness. That one actually has a jump in it. The second kernel you see there is the Gaussian kernel, which is very popular. The bottom left is something called the Epinetchnikov kernel, which is just an inverted quadratic, and it turns out to have certain optimality properties. And then the last one is called the tricube, which is just kind of an inverted cubic thing. Okay, so there's many different kernels. The choice of kernel turns out not to matter very much. If you want to have a fixed idea in your mind as we go along, I would just suggest think about the normal kernel. The reason for making it symmetric, though, is a little bit subtle. It's got to do with when we do the bias calculation, we're going to see that we get a faster rate of convergence precisely because we've chosen a symmetric kernel. So that'll come up in a minute when we do the analysis. So keep the symmetric in mind. All right, and then the estimator itself, you've probably seen this before, is fairly simple. We just take the data points. Here's the data. The way I like to think about it is we start with a piece of mass of 1 over n on each data point. Think of it like a toothpick of mass 1 over n. And now think of it, I always like to use the analogy, think of it like cheese, actually. A piece of cheese of 1 over n, and now you start to melt the cheese. So we're going to smooth it out by melting these things out, like this. These are the kernels. I'm just placing a kernel on top of every data point. That's kind of like the smoothing operation. And then we now define the density estimator at any given point, x. So don't confuse the data, which are just endpoints, and then the target point, x, where we're estimating the density, can be any point at all. It doesn't have to be one of the data. And we define the density estimator to be the average of the contributions of all the different kernels. So in symbols, we have x. Looks like this. I'm going to write it for one dimension for the moment. What I've done is I've introduced here this h, which is called the bandwidth, which is just a rescaling of the kernel. So again, if you keep the normal example in mind, this is just the standard deviation of the normal. I put the h in here to rescale it. Why do I put a 1 over h up front? To make sure it still integrates to 1. So this whole thing, each one of these integrates to 1, and it's an average, so if you integrate this, it integrates to 1. And all the h is doing is when h is small, I'm putting very peaked kernels. But when h is big, I'm putting very broad kernels. This is what's controlling the amount of smoothing. In histograms, it was the size of the bins. Here it's the size of the kernel. It's the bandwidth. That's our smoothing parameter. So that picture there shows you an example in figure 3. You can see each data point. There's a kernel sitting on top of them. And then I averaged it, and then I actually made it, that density estimator that you're seeing there probably doesn't integrate to 1. I had to lift it up so you can see clearly what was going on. But in principle, this integrates to 1. So let's think a little bit about the limiting cases. What happens to this estimator as h goes to 0 when I make the down go to 0? What does this density estimator look like when h goes to 0? Oh, I just get these spikes again, right? Just like before. A useless density estimator. I'm undersmoothing. What happens to this estimator as h goes to infinity? It becomes more and more uniform. That was the original picture I showed you of the Bart-Simpson dense distribution at the beginning of class. That's what those different estimators were. They're just 3 different kernel density estimators with a small, medium, and large bandwidth. And you can see that choosing the bandwidth is critical. In fact, a good exercise is if you use the function density in R, it will do a density estimator for you. And you can pick a bandwidth, and you can pick a different kernel if you want. And what you'll see is if you change the kernel shape, it doesn't really change the estimator very much. But if you change the bandwidth, it's completely different. So the real hard thing here is picking the bandwidth, not picking the kernel. Okay, so is the definition of the kernel estimator clear? Any questions of the definition? Yes?
So, can we choose a kernel such that this reduces back to the histogram?
No. So this will never give you a histogram. And the difference is this. for a histogram, we always have these fixed bins. If I were to use the boxcar kernel, that is like putting a bin, right? Because I'm putting a boxcar over each observation. The difference is, it follows the observations. Over each observation, you have a boxcar. They would even overlap. They would never split into separate bins. Yeah, so a boxcar kernel gives you a kind of a lumpy density estimator that's still a kernel density estimator, sort of histogram-like, but it's not a histogram. It's precisely this property that the kernel follows the data points and that it's symmetric around each data point that you can see is going to give us a faster rate of convergence. Let me say that in the multivariate case, well, how are we doing on time here, though? Okay, 4 minutes. In the multivariate case, in principle, you don't have to use a single bandwidth. You can use a matrix of bandwidth. So in general, you can have a bandwidth matrix. This would be a positive definite symmetric matrix. And the estimator would look something like this. It would still just be an average of these things. Let's say they're called the case of H. Where the notation here, case of H is going to be scaled, so it's going to look like this. The determinant minus a half. So if these are the data, the way to think about it is I'm plopping a kernel on top of each data point, and this I might want to use a kernel that looks like this, and so that would be some weird matrix H. But in practice, people don't usually use it in such great generality because now it's going to be hard to pick the bandwidth. Picking a whole matrix full of bandwidths is going to be really painful. So a common thing to do would be to scale all the variables to have be on the same scale, and then take a diagonal bandwidth matrix. In other words, the multivariate version that's most commonly used would look like this then. So if I did that, I only have one number to pick still. But in principle, you could use a much more rich family of multivariate estimators. When we do the analysis, we're going to just do the analysis for this estimator. And so again, it's like plopping a kernel on top of the data points and averaging them. It's still the same basic principle as the one-dimensional. So let me give you the game plan then. We're running out of time, but I'll finish this up on Monday. We're going to go through the mean and the bias and variance and the minimax stuff. It gets a little bit more complicated, but the same kind of principles apply. I'll just tell you that this is what I'm going to tell you right now that the rate of convergence, because you're going to see this all throughout the course, is going to be something like 2 beta over 2 beta plus b, where roughly speaking, beta is the number of derivatives you're assuming the density. So if you assume 2 nice derivatives for the density, this beta would be 2. So like in one dimension, this would be 1 over n to the 4/5, compared to 2/3 for the histogram. The reason why we get faster rate of convergence is because we'll be making a stronger assumption about the density, namely that it's smooth, and the design of the kernel. We'll see that when we do the risk analysis. So we'll finish that up. Then we'll talk about confidence bands. Then we're going to talk about cross validation, which is how to actually pick these things. And then we'll be moving on to the next topic. Any last questions?
Larry, I think Monday is MLK Day.
Oh. MLK Day. So it's Martin Luther King Day Monday, and we don't have class.
I think so, yeah.
Well, how about that? You already have a holiday. Okay, well, then I guess I'll see you next Wednesday.
Yeah, just business.